Welcome back to Lesson 8. In this video, we'll be focusing on the right side of this slide, which covers the entire value modeling task. We'll review the swing weight matrix and how to obtain global weights for each value measure. We'll discuss value functions, and we will put everything together into the additive value model. Our goal with the quantitative value model is to determine how well a candidate solution meets stakeholder values. We want to do this using a quantitative value model that can account for multiple objectives that may actually compete with one another. For example, we might be considering an unmanned aerial vehicle, or UAV, and have one objective be minimize weight and another objective be maximize weather conditions that it can operate in. A lighter weight vehicle may be able to operate in fewer weather conditions. So how do we handle that situation? We have two aspects of a quantitative value model. One is weights for the value measures that reflect the importance and variation of the value measures. The second is value functions that allow us to convert raw data to standard units of value and capture returns to scale on the value measures. Determining the weight or relative importance of each value measure is the first part of the quantitative value model. As you saw in Lesson 6, the swing weight matrix is used to record numeric values for each value measure based on the level of importance and variation in the measure range. These values range from 1 to 100, and they should decrease as you move from top to bottom in a column of the swing weight matrix or from left to right in a row. You can see in the example shown for the dining out decision that the stakeholder places high importance on the menu choices value measure and that it has a high range of variation. On the other hand, health score has a low importance to the stakeholder and the variation for the number of violations is low. Using equation 10.2 shown at the bottom right of the slide, we can determine the global weight for each value measure by dividing its swing weight by the sum of all of the swing weights. Here we see those calculations carried out, and we have the global weights for all 5 value measures. We also see that they sum to 1. Well, they would if we hadn't rounded them to 2 decimal places. Now we turn to value functions. Remember that each value measure has its own units that we show at the very bottom of the value hierarchy. And those units are most likely different. When we have a solution candidate that we are assessing, we'll get a raw score for a value measure in units of stars or level of pain as shown here, or miles per hour or pounds, or whatever the units of the different value measures are. We need to develop a value function for each value measure that converts those raw scores into value scores, so that when we combine them to determine the overall value for the solution, we are combining common units. The value function also needs to reflect what we call returns to scale. This means that the function needs to reflect how value changes as the raw score changes. You can see some typical value function types in the upper right of this slide. Some value measures will have linear relationships between the value scores and the raw scores. Other common relationships are concave, convex, or an S-curve. Note that the functions can be either increasing or decreasing. The curves on the left are for value measures where more is better, and the curves on the right are for those where less is better. In all cases, we need to choose a common scale for value, usually from 0 to 100 as shown here. A value score of 0 will correspond to the minimum acceptable value for the raw score of a given value measure, while a value score of 100 will correspond to the ideal raw score on a value measure. This range of raw scores, from minimum acceptable to ideal, will be the limits on the horizontal axis of a graph of the value function. The range of value scores from 0 to 100 will be on the vertical axis. Determining these ranges and the shapes of the graphs will require input from the stakeholders and decision makers for the overall problem. It may require a couple of iterations of input until they agree that you have accurately represented what they value in a solution. Once we have the weights and the value functions for all the value measures, we have all the information we need to apply the additive value model. This equation shows how we compute a total value score for a candidate solution. I'll walk you through it thoroughly and show how what we have done up to this point fits into it. First, on the left side, we have the total value, capital V, of the candidate solution, xj. We can assume that we have several candidate solutions represented by x1, x2, x3, and so on. This one is xj. The total value on the left is different than the value score. Here we have the value earned by the candidate solution j for performance against value measure I. So Vi of xji is in units of value, which is what we want. Wi is the value measure weight, the global weight, which is some number between 0 and 1. We multiply the weight by the value score, and we add up those products for all the value measures. Here n represents the number of value measures, so we would have n weight value score products that we would add together. Those value scores are determined using the different value functions for each of the value measures so that we have common units of value. The xji represents the raw score that the candidate solution j gets on value measure I. We'll take that raw score, we'll find its location on the horizontal axis of the value function graph for value measure I, and then we go up to the curve and over to the vertical axis to find the value score associated with the raw score. And that is the number that we use in the equation for Vi of xji. Next, we need the global weight to multiply it by. Recall that we used swing weights for each value measure to assess importance and variation. The value measure weights, or global weights, are simply the normalized swing weights. What that means is that we divide each swing weight by the sum of all the swing weights so that the results are all numbers between 0 and 1, and the sum of all the global weights is equal to 1. So we take the global weight for value measure I, and that's the number we use in the equation for Wi. We multiply Wi and Vi of xji, and then we sum those products over all n value measures. This additive value model is the most common value model used in military multi-objective decision analysis. The methods for obtaining the weights and value functions may vary, but the overall model structure is the same. So that you're clear on the different variables we've been using in the additive value model, let's review them. xji is the raw score of candidate solution j on value measure I. It is in whatever units value measure I is measured in, pounds, stars, miles per hour, etc. Vi of xji is the single-dimensional value of candidate solution j on value measure I. It will be a number between 0 and 100 and is determined using the value function for value measure I. Fi is the swing weight of value measure I. It's a number between 0 and 100 and will be shown on the swing weight matrix. Wi is the global weight of value measure I. It's a number between 0 and 1 and is found by dividing the swing weight Fi by the sum of all the swing weights. Finally, capital V of xj is the total value of candidate solution j. It is the sum of the products of the global weights and value scores across all value measures. That concludes the explanation of quantitative value modeling. In the next video, we'll work through an example.